ASAP can be used to analyze imaging systems, non-imaging systems, or illumination systems, as well as light concentrating devices. Let's take a look at an imaging system analyzed within ASAP. And in this particular case, what we're going to do is look at a singlet lens, but basically we've simply defined a singlet lens with a focal length of 100 millimeters made of BK7, and what we're going to let ASAP do is actually determine the best bend ratio for this system to give us the best performance over a 20-degree field of view. So I'm going to run the file, and then we can take a look at the results. And we initially started out with plain parallel plates and, of course, very poor image quality. And as we optimize the system, we can see that ASAP determines the appropriate shape factor to minimize our aberrations. And by coming back, and I'm going to look at my command output window here, so I'm going to enlarge that for a moment, and we can see information about the spherical aberration coefficients, chromatic aberration coefficients, etc. And we can also see information about the surface after the optimization. We started out with a lens that had a shape factor of 0, so it was a symmetric lens, and we see that the optimized lens has these particular values for the radius of curvature. So I now have not only analyzed the performance of the system, I've also optimized it totally within ASAP. Another type of system that's commonly analyzed using ASAP are non-imaging or illumination systems. And right now, let's take a look at a simple light pipe example. And in this file, we're going to define a light pipe, and we're also going to use an LED source model to send light through the light pipe, and we're going to look at the information ASAP can give us about the performance of that light pipe. This file is written in such a way that you actually can analyze many types of systems, either elliptical or rectangular light pipes. You can also choose different sizes of light pipes, different bend ratios, different bend angles. So this file can be used for many types of applications and analysis. But let's just run the file. And now we see the basic geometry of the system. And after ASAP draws the geometry, we'll be able to trace the rays and look at these results. And now we see the basic geometry that's making up our system, and shortly we will see the results of the ray trace analysis. And now we can look at the results of the analysis. This is the information about the energy leaving the output face of the light pipe. And in this particular case, we only chose to draw a small number of rays, about 10,000 through the system, through our rectangular pipe. And we can also look at it in an isometric form, a contour form. ASAP will allow you to look at this analysis in many different ways, and you can get significant amounts of information about the efficiency of this light pipe, leakage, etc. Another thing I'd like to look at is what's happening to the light within the light pipe. And we've actually saved quite a bit more data within this file. And I'm going to modify my file just to have ASAP perform these next couple of lines, which will allow me to see the energy as it propagates through the pipe itself. What we've done is basically saved information about the rays as they propagate through the pipe at many, many different locations. And what we see here is, for instance, the leakage that's occurring within the pipe. And we can move it around and we can see information about the rays anywhere within the pipe. But there are a couple of things we'll notice. And the first thing I'm going to do is hide the light pipe temporarily, or actually just turn it into a wireframe, so we can effectively look through the pipe. Because one thing we're going to have to do if we have a light pipe is mold into the pipe the locations of our connecting screws so we can mount it in place. And we want to make sure we do that at a location where there's not a concentration of energy, because we don't want that to be affected by our mounting hardware. And if we look, we see that there's very little ray interactions in this region, so this is probably an ideal place for our mounting hardware. The other thing we can do is, let me turn this around a little bit, and you'll see we have a series of planes cutting through the light pipe. I can remove a few of those simply by choosing to hide them. And then what I can do is actually take any of these planes and move them through the light pipe to give myself a better idea of what's happening at any location within the light pipe. So not only can I see what the output is, I can also get information about where my leakage is occurring, how much leakage is occurring, where I have very little energy, and where I have the most energy. Another type of system we can look at with ASAP are things like light concentrating devices. And in this particular case, let's take a look at a compound concentrator. And I'm going to run the file. And in this particular case, with a concentrator, they're normally defined by the input and output numerical aperture, the source angle. They can be solid or hollow concentrators. If it's a solid concentrator, I can provide the index of refraction. So what I'm going to do is let ASAP design for me a simple compound hyperbolic concentrator. So I'm just going to change this data entry and then just click on OK. And now ASAP has defined the geometry for my concentrator, and we can launch rays through the system. We can vary the angle of input, and we can do analysis at the output plane to determine what the efficiency is and any other information we might need about this particular concentrator, or we can use this concentrator as the input or output to any other optical system.